started generating functions. So I said you that generating functions are used to generate moments from those generating functions. We have three types of generating functions called moment generating function, characteristic function CF, cumulative generating function CGF. So we have already described that moment generating function of a random variable is indicated with mxt, where x is the random variable, t is parameter, okay, is defined as expectation of e power tx. It is the definition for moment generating function. You know that expectation can be resolved into either sigma or integral depending upon the nature of the variable. If x is a discrete random variable, we start with sigma and within the brackets we have e power tx, and you will write the corresponding PMF. If at all, if it's a continuous random variable, we will start with integral e power tx into f of x dx. So these are nothing but these are the definitions for MGF. So we have already discussed how to generate moments from this. Now we are going to discuss the properties of moment generating function. Okay, so the first property is nothing but for any constant c, okay, mx ct is equal to mcxt. So if you observe, generally moment generating function is indicated with mxt. If you put the constant with c with t, a constant c with t or x, both are same. So mxct is same as mcxt. So if you attach the constant here or with t, both are same. So let us see that very small one, mxct. So how a generating function is defined? Expectation of e power tx. So by multiply MGF is nothing but expectation of e power, the product of these two. So here the e power, you will get the product of ctx. Okay, so this is nothing but LHS. If you go for RHS, what is RHS? mcxt. Here c is with the variable. So again, random moment generating function is defined as mxt is equal to expectation of e power tx, the product of these two, which is nothing but cxt. I think these two are same, as the one right hand side of these two are equal. We can say that mxct is equal to mcxt. So whenever we attach a constant with x or with t, we will get the same results. This is first property of moment generating function. The second one is nothing but MGF satisfies additive property. Or reproductive property. It either satisfies the reproductive or additive property. Let us see what additive property is. Additive property is nothing but name itself tells that you are going to add two variables. That is, if x1 comma x2 are two random variables, then the moment generating function of these two means if you have only one variable, we call it is a generating function of x1. If I write x1 plus x2, it indicates the moment generating function of the sum of the two random variables x1 comma x2. If you consider any two independent random variables x1 comma x2, mx1 plus x2 is equal to mx1t into mx2t. So satisfying additive property means that the moment generating function of sum of the random variables is equal to the product of their MGFs. That is, the MGF of the moment generating function of sum of two independent random variables is equal to the product of their MGFs. Okay, satisfying additive property means that the moment generating function of sum of the random variables is equal to product of their individual MGFs. So let us prove this. Okay, it is given that x1 comma x2 are independent random variables. So if x1 comma x2 are independent, you know that expectation of x1 x2 using the multiplication theorem on expectations, expectation of x1 x2 is equal to expectation of x into expectation of y, or expectation of x1 into expectation of x2. So to prove this, let us consider the LHS, which is nothing but mx1 plus x2t. How do you define the moment generating function of mxt? We have defined as expectation of e power tx. Here multiplying the parameter and random variable. So in the similar way, expectation of e power, you need to multiply these two, t of x1 plus x2. By the definition of expectation of e power tx means you should multiply these two. So expectation of e power tx1 plus tx2. Okay, I have multiplied these two, and also I can write this as e power tx1 into e power tx2. As a power n plus n is equal to a power m into a power n, I wrote like this. So here it is given that x and x1 comma x2 are independent. Whenever x1 comma x2 are independent, we know that e of x1 x2 can be written as e of x1 into e of x2. So this is nothing but e of tx1. We can write this as, if they are not independent, we cannot write in this way. Whenever they are independent only, we can write e of x1 x2 is equal to e of x1 into x2. So I have splitted since x1 x2 are independent. So I think this stands for mxt, am I right? mx1 of t. This is nothing but into mx2 of t. So we have proved that mx1 plus x2 of t is equal to mx1t into mx2t. Hence we can say that MGF satisfies the additive or reproductive property. So after discussing the moment generating function, the second generating function we are going to discuss is nothing but characteristic function, which we indicate with CF. Moment generating function is indicated with denoted with MGF. Characteristic function is denoted with CF. If you take any random variable x, moment generating function is indicated with mxt. Characteristic function is indicated with phi xt, which is defined as expectation of e power itx, where I is the imaginary number. I think there is no change in the additive and in the MGF and CF. We have defined mxt, moment generating function, expectation of e power tx. If we observe these two, this is MGF, this is CF. Both are almost all same, except that in place of tx we have I, which is called the imaginary number. Phi xt is called the characteristic function, which is defined as the product of e power tx, but we have I here. Why? Because why we have another form of this characteristic function is nothing but, as you know that all these generating functions are used for generating moments. Okay, so in some cases we use MGF, in some cases we use the characteristic function, depending upon the PDF given to you. Now let us see how to derive moments from this. Okay, for all these generating functions the same, how to find moments from CF. I think for MGF also we did the same. We have defined MGF, then we went for how to derive moments from this, and then the properties. For CF also definition, how to derive moments and properties. So let us see how to derive moments from it. So we are indicating the MGF with expectation of e power itx. Okay, itx means if it is a discrete random variable, I think you'll write the same thing whatever we have within the brackets, and we'll start with sigma with p of x. If it is a continuous random variable, you'll start with integral, whatever we have in the brackets you'll write the same along with the PDF. You have described the definition for a phi xt in case of discrete and continuous random variable. Let us see how to find moments from this. To find the moments from it, okay, How we have calculated moments from mxt? We have calculated moments from mxt by taking the coefficient of either t power r by r factorial or finding the derivative with mu r dash is equal to d power r by dt power r mxt. Girls, one more notice that please try to watch the previous videos. Okay, directly you cannot understand characteristic function, directly you cannot understand the cumulant generating function. So as you have already the videos are with you, just go try to go step by step. Okay, don't watch as I am sending this video today, don't directly click on this video, just go back to the previous moment generating function definitions and properties, then come to characteristic function. Again similarly, while dealing with cumulant generating function, directly don't go to the cumulant generating function video itself, just go through the previous videos. Okay, that gives a good results. Don't go directly, you don't understand anything at all. As the classes are in the form of videos, I think you can recollect by watching them. Okay, otherwise just clicking on the video is useless for you. Okay, now let us see how to find the moments from this. So to calculate the moments from this, we know that e power, what is the expansion for this? E power x is, because the same thing I have discussed in MGF also, this is the expansion for e power x. So if I go for e power itx, in place of x we have itx. So this will be 1 plus itx plus itx whole square by 2 factorial plus itx whole cube by 3 factorial and so on. So if you take expectations on this, what is phi xt? Phi xt is nothing but expectation of e power itx. So if you take the phi xt, here becomes phi xt is equal to expectation of 1 plus itx whole square by 2 factorial, and you have many more, it's an infinite series. So you know that by using the addition theorem on expectations, expectation of xy is expectation of x plus expectation of y. So using that I can write this in this way, and so on. We have many more terms there. What is expectation of a constant? Is again constant. What are the two constants here? X is the only variable, I and t are nothing but constants. So we can take out those two out of the expectation of x. As I said you, I square is a constant and t square is a constant. We can take it out of the expectation and so on. So what is expectation of x is nothing but mu1 dash. Expectation of x square is nothing but mu2 dash and so on. Expectation of xr is nothing but mu r dash. So phi xt is equal to, we got this as 1 plus it mu1 dash plus I square t square by 2 factorial into mu2 dash and so on. So as you know that while calculating moments, first we calculate the non-central moments and then we go for central moments. So how can you get mu1 dash here? Mu1 dash is nothing but coefficient of it. How do you get mu2 dash from this expansion? Coefficient of I square t square by 2 factorial is mu2 dash. Similarly mu3 dash means I cube t cube by 3 factorial. So you will get mu1 dash is equal to coefficient of it. Mu2 dash is nothing but coefficient of I square t square by 2 factorial. Mu3 dash is I cube t cube by 3 factorial. In general, mu r dash is nothing but I power r t power r by r factorial. So after calculating the non-central moments, you can go for central moments by using the interrelationship them. So to calculate moments from this, I think the similar steps we have done with the moment generating function also, where we don't have I there. Coefficient of t gives mu1 dash, coefficient of t square by 2 factorial gives mu2 dash, t cube by 3 factorial gives mu3 dash, and coefficient of t power r by r factorial gives mu r dash. Means the major, as in the definition itself we have I here, everything is same. In place of t you are getting it. Similarly, to calculate moments, another way by using derivative is nothing but I power r into d power r by dt power r into 5xt at t is equal to 0. I think for to calculate from mxt, we don't have this here, d power r by dt power r mxt at t is equal to 0. So if you can understand the mgf, cgf is also similar, except in place of t we have it. So let us discuss the properties in the next class. Okay, thank you.